This is page 24 of the Extension 2 Polynomials booklet. Okay, example 2. Use de Moivre's theorem to express tan 5 theta in terms of powers of tan theta. Hence show that x to the power of 4 minus 10x squared plus 5 has the roots plus or minus tan theta and plus or minus tan 2 theta, etc. Then you'll be deducing this result. Can you see that this result is a what? A product of roots. I know that there's 4 roots because that's an x to the 4, all right? So, yes, all right, equals. So we're starting with the result. Just remember what it is. It's r to the n cis n theta equals r to the n, all of it, cis theta to the power of n. Okay, so that's what we're using. So we're going to go cos of 5 theta plus I sine 5 theta. This is your de Moivre's theorem way, where you've got 1 to the power of 5 out the front, equals cos theta plus I sine theta to the power of 5. Now I'm just going to rearrange the, I'm going to need a lot of room, so I'm going to have to move over. I'm going to expand the right-hand side. Remember Pascal's triangle. If you can remember from 1, 3, 3, 1, what's after that? That's right. Even if you can remember that, even better. You just got to go one more step. What's the next one after that? Yeah. So if you remember 1, 4, 6, 4, 1, then we've got 1, 5, 10, 10, 5, 1. You only need to remember the 1, 5, 10. Then it just goes back down. Okay, 10, 5, 1. 6 terms for the expansion to the power of 5. Actually, all the odd expansions are the easiest ones because they've only got a few numbers to remember because they go up and down and they're symmetrical. Okay, so therefore we've got cos to the power of 5 theta plus 5 cos to the power of 4 theta I sine theta. Now, we can go, all right, we'll put the I squared, or you just want to put the minus in straight away. Plus 10 cos cubed theta I squared sine squared theta plus 10 cos squared theta I cubed sine cubed theta plus 5 cos theta I to the power of 4 sine to the power of 4 theta plus sine to the power of 5 theta equals I 5 sine to the power of 5 theta. Next, right, we've got cos to the power of 5 theta plus, or either we put all the I ones together and the real ones together, it doesn't matter, plus 5, I'm going to put the I on the end, cos to the power of 4 theta sine theta I. Then we've got minus, because I squared is negative 1, minus 10 cos cubed theta sine squared theta. Then I cubed is negative 1, so we've got minus I. But I'm going to put the minus at the front, but the I on the end, minus 10 cos squared theta sine cubed theta I. Then we've got I squared is negative 1 twice, which brings us back to positive 1. So plus 5 cos theta sine to the power of 4 theta. Again, I squared is negative 1, I squared is negative 1, positive 1, plus I. Plus sine 5 sine to the power of 5 theta I. Getting real and imaginary parts, we'll do the real ones first. Cos of 5 theta is equal to cos to the power of 5 theta plus, minus 10 cos cubed theta sine squared theta plus 5 cos theta sine to the power of 4 theta. And now the imaginary parts, sine of 5 theta is 5 cos to the power of 4 theta sine theta. That's that first one from there, from here. Then we'll take this one here, minus 10 cos squared theta sine cubed theta. And the last one is this last term here, plus 5 to the plus sine to the power of 5 theta. We call that equation 1, and this equation 2, of course, we've got to do equation 2 divided by equation 1. So therefore tan 5 theta is sine of 5 theta over cos of 5 theta. All good? Which is, now we're going to write that all out, 5 cos to the power of 4 theta sine theta minus 10 cos squared theta sine cubed theta plus sine to the power of 5 theta all over cos to the power of 5 theta minus 10 cos cubed theta sine squared theta plus 5 cos theta sine to the power of 4 theta. Notice I have combinations of sine and cos for every term. I must divide by the highest power of cos, which is cos to the power of 5 theta. And you'll see what happens. They'll all change to tans. So divide through by cos to the power of 5 theta. And you will get, now I need to do numerator first, then denominator. Divide through each term in the numerator and each term in the denominator. What would happen here? Won't you just get 5 sine theta on cos theta, which is what? 5 tan theta. For the next one, if you put that over cos 5 theta, cos to the power of 5 theta, 2 of the powers cancel and you've got sine cubed theta on cos cubed theta. Does that make sense? So you get minus 10 tan cubed theta. Do you get that? Yeah, if we divide this one by cos to the power of 5 theta, we get plus tan to the power of 5 theta over, right, dividing this by cos to the power of 5 theta gives me 1 minus, divide this by cos to the power of 5 theta, 3 of them cancel, 10 tan squared theta, and divide the last term by cos to the power of 5 theta, 1 of them cancels, plus 5 tan to the power of 4 theta. Now that's what tan of 5 theta equals, okay? So therefore, tan of 5 theta equals that. Notice it's saying, hence show that x to the power of 4 minus 10x squared plus 5 equals 0 has these roots tan of plus or minus 10 2 pi over 5. We're going to have to let x equal something. Remember, in the other one we let x equal cos theta. This time we're going to let x equals tan theta. Notice if x is tan theta, I'm going to get 5x to the power of 4 minus 10x squared. I know I've got a 1 here, but, you know, something will work out. So what we're going to do is let x equal tan theta. Therefore, and now if we do that, there is a trick here. Then, so we're saying let x equal tan theta, but we're also going to let tan of 5 theta equal 0, okay? So, if we let tan of 5 theta equal 0, so if tan of 5 theta is 0, don't we multiply that by that, and we get, so therefore, therefore 5 tan theta minus tan cubed theta plus tan to the power of 5 theta equals 0. Because the denominator here is not allowed to equal 0. Alright? I can't say that that is 1. We've got a common factor of tan theta. Now let's, I haven't actually substituted my x is tan theta. So I'll do it now. So therefore 5x minus 10x cubed plus x to the power of 5 equals 0. Now we can take out x as a common factor. We would never divide through by x. So x bracket 5 minus 10x squared plus x to the power of 4 equals 0. Now that is, hence show that x to the power of 4 minus 10x squared plus 5 equals 0. We're coming up with that equation. All right? So, if I want to solve that, the reason we're putting this equal to 0 is we're trying to find the roots of the polynomial. That's why. So when you get a polynomial, put it equal to 0, you're finding the roots of the polynomial. But because all of that equals tan phi theta, we just say let tan phi theta equal 0. Of course, the numerator is the one that's going to have to equal 0, not the denominator. So, hence, the roots of x to the power of 4 minus 10x squared plus 5 equals 0 are the non-zero values of tan theta. Now, I'll explain what that means. You know how x equals tan theta? So I've got basically here that tan theta equals 0, or x to the power of 4 plus 10x squared, x to the power of 4 minus 10x squared plus 5 equals 0. If x equals tan theta, x is tan theta, so tan theta is 0. According to the tan graph, tan of 0 is 0. Got it? Okay, that's what that means. So these are the non-zero values of tan theta. All right? So if this bit's 0, then this is not going to be 0, this whole thing as well. Because 0 times anything will give you 0. Got it? What we're saying here is, therefore, tan theta is 0, or tan 4 theta minus 10 tan squared theta plus 5 is 0. Tan theta is 0. The only solution is 0. Yes, it's also pi and whatever, because tan of 0 is 0. So therefore, the roots of this are the non-zero values. If that's 0, we don't. You know how when you first learned how to solve quadratics, you would say, therefore, x is 2 or 3 to give the 0 for your whole quadratic. That's what we mean. If that one's 0, this is not. So sorry if I'm repeating myself. Hence, the roots of x to the power of 4 minus 10x squared plus 5 equals 0 are the non-zero values of tan theta. Because if tan theta is 0, then theta is 0. Okay? Where theta is a solution of tan 5 theta equals 0. But remember that we let tan 5 theta equal 0. When you look at that, isn't that looks like one of those general solution type questions? So if you want to solve that, we'd give the general solution to that. So therefore, what's the general solution for the tan one? Isn't it 180n plus pi? Right? So the general solution is, but I don't have to give the general. I can start listing out lots of solutions. Remember, I've got to give the first 5. I need to give 5 solutions. So I can either go general solution, or I can just list 5 solutions, more than 5, and eliminate the doubles. Got it? So what are we doing? Remember in complex numbers we did it using general solution? You can do general solution if you want. Do you like general solution? Remember this is the tan curve and it repeats every 180. So this is 0, pi, etc. The next one would be a 2 pi, etc. And then you'd have other solutions back here at where? Negative pi, etc. So we've got two choices here. If we want to do general solution, we go, remember you've got the formula sheet. It's 5 theta for the general solution is pi n plus tan of what is 0, 0 plus 0 where n equals 0 plus or minus 1 plus or minus 2 and so on. So therefore 5 theta equals. So let's start listing them out. You can do 1, 2, 3. K, do you want a K? Because this is how you put what they are. So therefore 5 theta is 0 plus or minus pi plus or minus 2 pi, etc. Okay? So therefore theta is plus or minus, just 0 because we're dividing by 5, plus or minus pi on 5, plus or minus 2 pi on 5, etc. Okay? I mean, I can keep going. You know what I mean? Plus or minus 3 pi, etc. 4 pi, etc. plus or minus 3 pi and 5, plus or minus 4 pi and 5, etc. Now, I don't say which ones are the double ups till I stick the x's, so I make it tan theta. So we know, but we only have 5 solutions, and then we see which ones are the double ups. All right? All right, so our roots, remember, but, that x are the roots. So x equals tan 0, tan plus tan pi on 5, tan minus pi on 5, tan 2 pi on 5, tan of minus 2 pi on 5. And let's just see where they are, all right? So tan of 0, fine, all right? Tan of pi on 5 is where? 1/5, quadrant 1. Tan of 2 pi on 5, quadrant 1, right? Tan, if I did do tan of 3 pi on 5, that's in quadrant 2, which is the same as negative, so that's pi on 5. This is 2 pi on 5. If I did want to do 3 pi on 5, that's a quadrant 2 angle, which I need to be representing as a quadrant 1 or 4 angle, which are acute angles. Isn't that one the same as, here's my negative pi on 5, and there's my negative 2 pi on 5. Well, quadrant 2, tan is negative, that's 2 pi on 5. Tan of 3 pi on 5 is the same as tan of negative 2 pi on 5. Get it? All right, so I don't need it. Tan of negative 3 pi on 5 is the same as negative tan 2 pi on 5 as well. All right, so they're my solutions, since tan of 3 pi on 5 equals negative tan of 2 pi on 5. Do you know what I mean? And tan of, say, negative 3 pi on 5 is also equal to negative 2 tan of 2 pi on 5, etc. Got it? And all those other roots are doubles ups as well. Tan of 4 pi on 5 is negative tan of pi on 5. And same with tan of negative 4 pi on 5 is also negative tan of pi on 5, etc. So these are your roots. Solutions, roots to your equation. Remember, tan 0 was the solution for this is x equals 0 here. And the x to the power of 4 plus 10x squared minus 10x squared plus 5 has these 4 solutions. So that is your solution to the x is 0 bit, this bit. And these are your solutions or roots to x4 minus 10x squared plus 5 equals 0. Do you get it, that those 4 are the other solutions? Remember we said these were the non-zero solutions? Because if you work out tan pi on 5, you don't get 0. If you work out tan of negative pi on 5, you don't get 0. But if you do tan 0, you get 0. So this was the other solution to this bit, x is 0. That's my solution to that. These are my non-zero solutions. Do you see what we mean? Because if you evaluate the 4 other solutions, you don't get 0. Tan 2 pi on 5 is not 0. They are the non-zero solutions. And tan of negative 2 pi on 5 is also not 0. Actually, girls, how am I supposed to write tan of negative pi on 5 anyway? I need to rewrite those. That's not how the answer is. So isn't that tan of pi on 5? Isn't tan of negative pi on 5 quadrant 4 the same as negative tan pi on 5? Because, you know, you note that tan of negative pi on 5 is equal to negative tan pi on 5. See how they're saying show that the roots are plus or minus tan pi on 5? Not show that the roots are tan pi on 5, tan minus pi on 5, tan 2 pi on 5. They're not saying tan of negative 2 pi on 5. We just need to say down here that notice that tan of negative pi on 5 equals negative tan pi on 5. And also notice that tan of negative 2 pi on 5 is equal to negative tan 2 pi on 5. Are we okay with that? Note. Therefore, the four solutions, sorry, I've made a big mess, all right? We good with that? So you must say that. Notice that tan of negative pi and 5 equals tan of negative pi and 5 is negative tan pi and 5. We're talking quadrant 4, remember? That result holds for sine and tan in quadrant 4, but not for cos. And tan of negative 2 pi and 5 equals that. You can say that these are quadrant 4. So therefore, you get those four solutions. Sorry, I did go on to the next page and didn't record. Next part of the question was to deduce that tan pi and 5, tan 2 pi and 5 times tan 3 pi and 5, tan 4 pi and 5 is 5. Now, I'm not going to write that out again. I'm just going to say that the left-hand side, the tan pi and 5 and tan 2 pi and 5 are the same, but we know from earlier on this page that tan of 3 pi and 5 is negative tan 2 pi and 5, and that the tan of 4 pi and 5 is negative tan pi and 5. Now, that happens to be the roots that we found in the earlier part. Therefore, that's really asking you for the product of the roots, which is e on a, and if you go back to the original equation, e is 5, because it's a, b, c, d is 0, and so is b, and e is 5 and a is 1. So it's 5 on 1, which is 5. So therefore, we've proven that those things multiplied by each other, actually nearly done. What haven't I done? The two negatives make up positive. Yeah, no, that's fine. Actually, it's done. It's done. That it's equal to 5. Now, the last part of the question is to solve x to the power of 4 minus 10x squared plus 5 equals 0 another way. Have a look at it. What sort of equation? Quadratic. Quadratic. So x squared equals negative b, which is 10, plus or minus the square root of b squared, which is 100, minus 4 times 1 times 5 over 2 times 1, which is 10, plus or minus the square root of, isn't that 80? Square root of 80 is 16 root 4 root 5, plus or minus the square root of 80 over 2. So x squared equals 10 plus or minus 4 root 5 over 2. X squared is, can't I divide those both by 2? Isn't it 5 plus or minus 2 root 5? And so therefore x equals plus or minus the square root of 5 plus or minus 2 root 5. Now, we've got x equals square root of 5 plus 2 root 5. X is the square root of 5 minus 2 root 5. Can you see that? X equals negative square root of 5 plus 2 root 5. Can you see it? And x equals negative square root of 5 minus 2 root 5. You actually have 4 solutions there. And you've got this, which is another 2. Now, if you actually just want to check that that's correct, remember, why don't you just try and evaluate using radians, tan pi on 5, get an answer, and then just evaluate, say, now tan pi and 5 and tan 2 pi and 5 are quadrant 1 results. They're positive. These other two, negative tan 2 pi and 5, negative tan pi and 5, are negative results. So girls, the first one here, so can someone just do tan pi and 5? Let's just check. Tan pi and 5 is what? Etc. Now, can you just work out the square root of 5 plus 2 root 5? Do 5 plus 2 root 5 first and then square root it. Do 5 minus, so do 5 minus 2 root 5, get an answer and square root it. That's it. So notice that that is equal to square root of 5 minus 2 root 5. And I'd say that the tan 2 pi and 5, which was the, is the other one. 3.077 is the root 5 plus 2 root 5. And of course the negative ones would be the other two.